First, thank you for coming. Our next speaker is very well-known American theoretical physicist, Professor Michael Peskin. He has kindly agreed to visit us and join our school. But Professor Peskin indeed does not need much introduction. He is very well-known in the field, at least for his famous book on quantum field theory. All of us know this book. Just a few words I want to say. He was an undergraduate at Harvard University and obtained his PhD at Cornell University studying under Kenneth Wilson. He is currently a professor in the theory group at SLAC, National Accelerator Laboratory. He is a fellow of American Physical Society, fellow of American Association for Advancement of Science, and fellow of the American Academy of Arts and Sciences. He is also a noted advocate of building a future linear collider. Michael Peskin's research interests include all aspects of theoretical electromagnetic physics, but particularly the nature of new elementary physics. And it is a fortunate case, today he will lecture namely about this. So, please join me to welcome Professor Michael Peskin very warmly.
Okay. Very good. Thank you very much. It's a pleasure to be here. So this is the first of 4 lectures, actually. The general subject of these lectures is the problem of the symmetry breaking in the electroweak interactions and the Higgs boson. So why don't we begin? Let me just say, please let me know if the level of these lectures is not correct. I just have to guess. I met some of you. Your backgrounds are very, very different. If the level is too high, certainly let me know. If the level is too low, then I'll be here the whole week of the school, so we can discuss in any depth that you would like. So in any event, let's start out with this. So elementary particle physics really started in the beginning of the 1950s. And at that time, literally nothing was known about the subnuclear forces. It was known that there were nuclei, they had some spectroscopy. The forces that bound up those nuclei were definitely not understood. It was also known that there were radioactive decay processes, which could be parametrized phenomenologically by the famous Fermi 4-fermion Lagrangian. Also, the nature of those interactions was not understood. But gradually, as people began to learn about the physics of elementary particles, as accelerators produced the hadron spectrum, the muon was discovered, eventually the quarks were discovered, people came essentially in the 1970s to this model called the Standard Model. The Standard Model is Yang-Mills gauge theory with the group SU3 cross SU2 cross U1, as it says here. And basically, we now understand, and actually we understand with increasing precision, that this choice of a gauge theory of SU3 color cross SU2 cross U1 really answers these questions. And I'll, in the course of these lectures, show you some evidence for that, which, as I say, has become increasingly strong over the years. Now, does this mean that elementary particle physics is over? Well, that never happens in physics, because every time you peel off a layer of knowledge, there's another layer of ignorance underneath. Except that when you learn something, you learn to ask new questions. And there are new questions that are hidden underneath that now are exposed, and then it's very important for us to try to answer them. So what I'd like to do in these lectures is to discuss this basic understanding. So first of all, at least a few of you are not so familiar with the structure of the standard model. Here we'll be mainly concerned with the structure of the weak interactions, which are described by an SU2 cross U1 gauge theory written down by Glashow, Salam, and Weinberg. So in the first lecture, what I'd like to do is to tell you what the experimental basis is of this SU2 cross U1 theory, and to convince you that the experiments say that it really works extremely well. And I don't know how many of you feel that you have expertise in experimental particle physics. Could you raise your hand? I suspect that not many people in this audience will raise their hand. Experimental particle physics, even if you're a theorist, it's very interesting because the results are very beautiful. And I'll try and bring that out in the course of this lecture. It's also very hard, and I hope I'll explain that too. In the second lecture, I'd like to now say, on this basis, where do we go? And I'd like to explain that this SU2 cross U1 theory, despite its success, has important gaps that have to be filled. And so now we have to think about how to fill them. And I'll write down some proposals. Actually, I'll write down a very large number of proposals. I won't have time to explain them in detail, but maybe those of you who would like to be experts in this field, we can talk about them offline. In lecture 3, I'm going to discuss the Higgs boson. The Higgs boson it's a new particle from the point of view of experimenters. It was discovered at CERN, at the Large Hadron Collider, in 2012. Of course, for theorists, it's an old particle, having been originally postulated by Steven Weinberg in 1967. And essentially, people have been looking for it ever since, and it took a long time for experimenters to finally succeed. So I'd like to discuss the discovery of the Higgs boson. I'd like to discuss the properties that the Higgs boson is predicted to have within the standard model of particle physics. And I'll discuss the current information on this particle that we have from the LHC experiments. Then in the last lecture, I'm going to discuss why we need to go further, why it's interesting to study the Higgs boson in more detail. In particular, we have to hook up the information here with the questions from here. I'll try and explain to you that there's a mismatch, actually a somewhat severe mismatch, which I hope to repair. And we'll talk about experiments in the future that will go toward that. So that's the outline of this set of lectures. Okay. So let me now do a lightning review of the theory of the SU2 cross U1 model. And I'm going to write a lot of formulae in the next few slides. I was rather hoping that most of you have seen these formulae before in your particle physics or quantum field theory classes. But let's just go through. You write down the Glashow, Salam, Weinberg model. You derive its consequences. If you open my book to chapter 20, it's all kind of there. And here are the formulae. So first of all, it's an SU2 cross U1 model. So there are 3 + 1 or 4 vector bosons. Those are the photon, the W+ and W-, and the Z boson. The parameters of the theory are, first of all, because nothing can get mass unless the symmetry is broken, a vacuum expectation value, V, of the Higgs field, whose value we know is pretty close to 250 GeV, and coupling constants for the SU2 and U1, which are called G and G prime. This is the mass formula for, at the tree level, for the photon, the W's, and the Z. The photon is naturally massless in this model, as it must be, because we've never observed a photon mass. And the Z is a little heavier than the W. We'll talk about that quantitatively later. The A and Z are mixtures of the more fundamental SU2 and U1 bosons, and the mixing angle is characterized by this parameter, sine theta W, which is equal to G prime over G squared plus G prime squared, the square root. In the following, theta W will appear in basically all the formulae. And so I'm going to abbreviate the sine of theta W by SW, the cosine of theta W by CW. Please notice that the ratio of these two masses is actually the cosine of theta w, the cosine of the corresponding angle. It turns out that this relation is very important. It's obeyed experimentally to a couple parts per mil. And so that's not often natural in theories of physics, especially beyond the Standard Model. And it'll be an interesting criterion to apply to a theory that goes beyond the Standard Model, whether this relation is still satisfied. It's an interesting story. We'll talk about it in the next lecture. OK, now the couplings. Well, the photon couples to this set of charges. Remember, there's an SU2, so I'll call that I. And a U1, I'm going to call that Y, or hypercharge. The electric charge turns out to be I3 plus Y. The coupling strength is given by this formula, and that's what we call E. E is the strength with which the electron couples to the photon. Q is the electric charge, and those are, of course, 0 for neutrinos, -1 for electrons, 2/3 for the up quark, etc. W couples only to SU2, and it has a universal strength, which is G over the square root of 2. Here's the relation, again, between G and E. It's equivalent to that formula. The Z couples with a strength G over cosine theta W to this charge. It's similar to that one, but actually different. I3, which is something that is a property of the left-handed particles, not the right-handed particles. Sine squared theta W appears in the electric charge. So if you know the material on this slide, you can calculate the coupling of any boson in the theory to any fermion once you know its quantum numbers. And then you can work out cross-sections, branching ratios, anything you want. To complete the specification of the Standard Model, we need to know what fermions are involved. And as you all know, that's generations of fermions, which include an up quark, a down quark, a lepton, and the neutrino. And those have the quantum numbers that I've listed here. Please notice that the quantum numbers are different for the left and right-handed particles. Namely, the left-handed particles are assigned to doublets of the SU2, so I3 equals plus or minus a half. The right-handed particles are all assigned to singlets of SU2. And the hypercharge Y is such as to make the electric charges Q, which is I3 plus Y, come out right. So now we have a theory of the fermion vector boson couplings. We have assigned masses for the vector bosons. We have the quantum numbers which assign the values of those couplings. And now, what shall I say? Everything is predicted. So now what we have to ask is, does experiment actually agree with this and tell us that this is the correct model of weak interactions? Now, there are various ways to test this theory. And originally, it was tested at what we would now call relatively low energies with neutrino scattering, with various experiments on the weak interactions. Of course, radioactive decay, it's a part of this theory through W exchange. So that came in. Also, in 1982, the W and Z bosons were actually discovered at CERN in the proton-antiproton collider by colliding quarks and antiquarks. So these particles were seen as resonances. And the mass formula to the accuracy that they could be measured there agreed with what I've just presented to you. But really, the ability to go with high precision into the checking of these formulae came in the 1990s with a new type of experiment, which basically took electrons and positrons at high energy and collided them. Now, the Z couples to the electron, which means that one has a transition from Z to E plus E minus pairs, and therefore from E plus E minus pairs to Z's. And so if you then have an electron-positron collider, it has a fixed center of mass energy. You can adjust that to be the energy mc squared of the Z boson at rest. You would then produce individual Z bosons in the laboratory. You watch them decay, and in that context, you can verify all of the formulae that I've just presented to you. And in the rest of the lecture, I'd like to just go through and explain how that was done and how it works. So here, by the way, is the cross-section for electron-positron annihilation in the vicinity of 91 GeV, which is the mass of the Z boson. Please notice that this is a logarithmic scale. So from here to here, it's a factor of several hundred. And so at 60 GeV, you have a small cross-section. Just exactly at the mass of the Z boson, you find the resonance, and you have a large cross-section. The resonance you would think of as an ordinary nuclear physics type Breit-Wigner resonance, but there's more to it than that, as I'm just about to explain to you. Actually, the detailed shape of the resonance and, of course, its decay products all play into the testing of this SU2 cross U1 theory. By the way, this is the cross-section for hadrons. You can see the data here. Lower energy experiments are in good agreement with this part of the curve. This is the data for muons. Please notice that there's a relatively long tail, but if you if you insist that the muons take more than half the center of mass energy, you get a curve that looks very much like that. I think the difference between this and this has to be explained, and I will explain that to you in just a moment. Okay, so just a few more things. Once you have those formulae, you can work out what the prediction is for the partial width of the Z into every fermion species. Here's the formula. It involves a factor called alpha weak, which is G squared over 2, the strength of the intrinsic strength of the weak interaction. The number of colors comes in. This is the first order radiative correction to that. It's about a 4% correction here. We're going to do experiments much more accurately than that. The QZ, the charge, which is I3 minus sine squared theta W times Q, comes in here. The widths too, this is for left-handed species. The widths for right-handed species obey the same formula. And now, in order to get predictions, we just evaluate these formulae. A very convenient way to do that, oh, no, there's one more slide I wanted to show you. A lot of coupling constants are going to enter. And it's interesting to ask what the values of the coupling constants are. Actually, if we have a standard model that purports to be a fundamental model of particle physics, we should know what all the fundamental coupling constants are that appear in that model. And probably we wouldn't be surprised to know that those numbers are all of the same order of magnitude. So let me show you the numbers. Of course, you know that alpha, the strength of the electromagnetic interaction, is 1 over 137. But please don't take that too seriously. Alpha, as I hope you know, is renormalized. It's a running coupling constant. As you go to shorter distances, alpha actually gets larger. Essentially, a charge is screened by a cloud of electrons and positrons as you go deeper in mu plus mu minus quarks. As you penetrate that cloud, the apparent coupling gets stronger. When you come to distances of the mass of the Z, alpha is about 1 over 128. So that's actually the, if you like, the more fundamental basis that we can use to talk about the strength of the weak interaction couplings. From that, and the value of sine squared theta W, we have then the strength of those couplings. I'm not going to tell you where this number came from now, but it'll be pretty apparent as we go forward that it's coming from the data, and I'll show you many places where that number appears. This is kind of the world average of all of those things. Sine squared theta W, 0.23, that is a number close to a quarter. And that's probably something to memorize and keep in mind as I go through this lecture. In any case, combining this and this, what we find is that the weak interaction has a strength of about 1 over 30, and the U1 has a strength of about 1 over 100. So the weak interaction is weak, but it's not like tiny weak. It's not 10 to the minus 5 weak. It's weak, maybe not even as weak as ordinary electromagnetism, actually. Okay. It's interesting to compare this to the other important fundamental parameters. So alpha strong, computed at the same scale, is about 1/9. Actually, the strong interactions aren't much stronger than the weak interactions at the distance of the Z boson. And alpha T, which is the top quark Yukawa coupling, the top quark Higgs coupling, is about 1/13. So it's also roughly of this order of magnitude. So it's interesting. All of these numbers are the fundamental couplings of the strong interactions. They're all numbers of order 1, basically. And from those, using quantum field theory, you would derive the richness of the standard model. Okay, now here's the other thing to keep in mind. So what I'm going to do now is to take the QZs and I'm going to evaluate them. And then there'll be some systematics associated with that. So remember QZ, let me write it again here. QZ is the I3, which is plus or minus 1/2 for left-handed particles and 0 for right-handed particles, minus sine squared theta W, which has the value of about 0.23 times the electric charge. And then to get the quantum mechanical rates, you would square this and put it into a formula like the one I just showed you. So here are the values of the QZs written, again, just plugging into this formula. And then if you square them up, you get these values here. And probably I should explain to you what those values are. So SF is the sum of the squares. And that's going to give you the total rate for the Z to turn into that particular species. And AF is the asymmetry. Because as you saw, and we'll go back to this, the left couplings are different from the right couplings. And so that means that a Z is more likely to decay to, let's say, a muon, which is spinning in the left-handed sense, than a muon which is spinning in the right-handed sense. This is parity violation. It's the same parity violation as appears in the charge-changing weak interactions, the W interactions. But here we can really quantify it to a very nice degree. And so let's go back again. So the SFs determine the rates to go into each of these species. And as you see, these numbers are all roughly equal. The big number here is for neutrinos. The Z decays to neutrinos a lot. It decays about 20% of the time to one or another pair of neutrinos. And this is actually a very important thing for LHC physics. Whenever you see missing energy and you hope it's dark matter, usually it's a Z decaying to neutrinos. And you always have to keep that in mind. The A's are different. The A's have a large variation as you go across the various members of a generation. For the charged leptons, it's about 15%, the difference between the squares of these numbers. For down quarks, including the bottom quark, it's almost maximal. And it's funny that these formulae that don't seem to care very much about what species you have make such a large difference. And so the question, one of the questions we want to ask is, can experiment recover that when we actually measure the properties of the Z? Okay. So now let's start talking about this. Oh, here, no, there's still more introduction. Here are the branching ratios that you derive from those formulae. So basically, 6.7% for an individual neutrino. So if you take that times 3, it's the 20% I just quoted to you. 3.33% for the charged leptons. 15% for an individual down-type quark, including the bottom quark, although we'll have something little to say about that. The numerical value, when you add up everything, is 2.49 GeV. Actually, this is just a tree-level calculation. You can improve that if you compute one-loop radiative corrections. The measured experimental value is 2.4952 with a very small error. And the small difference between this and this is actually accounted for by the radiative corrections. So at this level, the theory is working extremely well. Now, to get this number is rather subtle. And I wanted to tell you a few things of the subtlety just to kind of impress you a little with what you have to do. Maybe I should also say what's on this slide. The radiative corrections in the electroweak theory are typically of order 1% and really have to be computed to make a precise comparison of theory and experiment. And I think in this lecture, I don't have much time to tell you how to do that. There's a little about it later in the lecture. One particular set of radiative corrections, though, which is very important, is the theory of the Z line shape, the line shape of the resonance. And so let me go into that in a little detail. So as I said before, ideally, the Z is a Breit-Wigner resonance. That is, this cross-section is proportional to this formula. mz squared is the resonance position in S. mz times gamma z is the width of the resonance. So gamma z is the width of the resonance. And what you would ordinarily do is you'd measure the cross-section as it goes up and down. You'd fit to this formula, and you'd extract the width. However, for the z, you don't actually get the right answer when you do that. And actually, you don't get the right answer by a large factor. And this has to do with the effect of what's called initial state radiation. That is, when you bring together electrons and positrons, they radiate photons in the process of annihilation. Those photons mainly go forward in one direction or another. And what they do is they decrease the amount of energy that the electron or positron carries into the reaction. So what that means is that you need a somewhat larger center of mass energy in order to produce a Z. So the Z, instead of having a nice normal resonance shape like that, ooh, this is not a nice pin. Instead of having a nice normal resonance shape like that, in fact has a resonance shape with weight pushed to higher energy and a long tail like that. And what you have to do is turn this into this by using QED theory before you measure the width of that resonance. So some numbers are here. The importance of this initial state radiation, photons radiated from the beams before they collide, is characterized by this number. There's an alpha, but there's also a log of S over ME squared, which is a kind of large number. And it turns out to be 10%. But that's not everything, because the Z is very narrow. And so actually a 1% energy loss can take you off the resonance. And so this number is enhanced by another number, which is the log of mz over gamma z. That's the log of about 100. And so when you put those two numbers together, what you find is that there's a 40% correction to the line shape that comes from this effect that you have to compute very carefully and take into account. And actually, it was some major work in the 80s and 90s to do these computations. There's a very beautiful paper by the Russian physicists, Fadin and Karayev, who thought about the initial state radiation in the way that you think about quarks inside a proton. They said, well, we start with an electron. The electron radiates photons, and it makes electrons that are kind of partons of the electron. And then integrating over all the photons, you would write the parton distribution of an electron in an electron. It turns out to be given by this formula where beta is the thing on the previous slide. And then you convolve those parton distributions to measure the distortion of the line shape. And other people later then refined this, and actually it really is computed now to relative order alpha squared times all logarithms of S over ME squared. Okay. The experiment is also very challenging for various experimental reasons. And that is that the LHC, or rather the LEP, which was the collider that was used to make these measurements. It's the electron collider that is in the tunnel, which is now the LHC tunnel. The tunnel is 27 kilometers around, and as you understand, it's kind of macroscopic. So it's subject to the effects of macroscopic things, namely heating and cooling, literally the phase of the moon, the effect of the tides on the rock and the water level in Lake Geneva, the seasonal variation of that Lake Geneva water level, all come into the calibration of the machine at the level we're now talking about parts in 10 to the minus 4. So let me just show you a few slides from that. This is pretty cool. This is the daily variation of the beam position, the equilibrium beam position in the LEP accelerator. And so the scale here is hundreds of microns. So by a fraction of a millimeter, the beam was going up and down. And the reason for this is the distortion of the large ring due to tidal effects on the rock in this macroscopic device. So one had to understand this and take it out in order to make a very precise mass measurement. Now you see, this is a day from midnight to the mid-afternoon. But then, actually, when they reached the high level of precision, the aim was really 10 to the minus 5 accuracy. They found this effect here, which is that the magnetic field was changing by millitesla in a very strange pattern over a very short period of time. This is 4 p.m. to 5 p.m. So the experimenters really had to work to figure out what that effect was, and was it a physics effect? How do you take it out? Do you just have to quote the entire range here as an uncertainty? This is the voltage on the beam pipe. It follows the same pattern. And by eliminating many possibilities, they eventually found this curve, which is the voltage on the rails of the high-speed train that goes from Geneva to Paris. So this is actually a little non-trivial. Here's the map. At 4 o'clock every day, the train à grande vitesse would leave the Cornavin station in Geneva and head out in a route like this toward Paris. It would create very high voltages in this region. Those voltages would then create currents that would try to go to ground. And the easiest way to go to ground, it turns out, was to go through the rock into the LEP ring, around to here, and short itself out in this river that goes to Lake Geneva. And so here's the predicted effect on the LEP machine from that effect. Indeed, the effect is really in this region. And in that way, they were able to understand and take out this particularly interesting systematic effect. The final result was, they're later. Yeah, here, the final effect result is this measurement. I'll show you, maybe I should show you the other one first, which is really something very beautiful. So you have sharp eyes. Would you tell your colleagues that there are error bars on those points? Do you see them?
I can see dots.
Yeah, you can't see.
I can see it there.
Yeah, you see this point has an error bar on it. Yeah, so that's the accuracy of the measurement. The black curve is this two-loop calculation that I described to you. They're in basically perfect agreement. It's really unbelievable. This is the Opal, which is one of the experiments at the LEP collider. It's really quite spectacular. The composite of the 4 LEP experiments is shown here. So the green curve is the measured curve. Here there are some error bars, and it says the measurement error bars are increased by a factor of 10, so you can see them. And then when you take out the initial state radiation effect, you get the red curve. And when you measure the width of the red curve, you get the number 2.495, et cetera, that I showed you before. So that's pretty incredible. Okay. We would also like to measure the branching ratios. And that's more straightforward. We collect Z events, we sort them into categories, and then each category, basically, you take an event, you throw it into a pile. Actually, of course, a computer does that. You sort them into a pile, and then the height of each pile gives you the branching ratio. Very nicely in this setup, and maybe I should emphasize this is not true at the LHC, but in this setup, the various branching ratios are very distinct, and so you can really sort them out. Here's one way of looking at it, which is you measure the number of charged particles from 0 to some high number, and you measure the energy in the charged particles. The QQ bar events end up as a big mound in the center. For the leptonic decay modes, there are only 2 particles, so they're here. The gamma gamma has no energy in charged particles. The leptonic decays are over here. Maybe a better way to look at it is to just visually look at these event displays. And you can see that they're, well, really different between electrons, muons, taus, and general hadronic events, which at this energy has this jet structure, which I think is the subject of a whole nother course in this summer school. The 2 jets here are the remnants of the quark and antiquark that are produced in the ZDK. There are a couple of these values that are actually interesting to think about. Let's think about what would happen if there were more neutrinos than just 3. If there were more neutrinos than 3, first of all, the width would be a little larger. It would be, an extra neutrino would make it 6.7% larger. And also the height of the cross-section would be smaller because this is the cross-section to hadrons, and some of the time the Z would be decaying to neutrinos. So this resonance would be distorted in a certain way. Because of the accuracy of the measurements, you can tell that that distortion isn't there. And so you can measure the number of neutrinos to which the Z decays, and here's the number. It's 3 with the accuracy in the somewhat lower than 1%. Another very interesting branching ratio is the branching ratio to bottom quarks. And the reason that this is interesting, especially interesting, is the bottom quark is the weak partner of the top quark. And we're going to see later in the lecture that the top quark is very likely a very weird object, which is maybe especially strongly connected to the physics of electroweak symmetry breaking. So that has the possibility that if the B can have a radiative correction which involves top quarks, maybe you could be sensitive to some new physics effects. Actually, even in the standard model, there's an effect. From these diagrams, it turns out that they create a correction to the formula that I wrote here, which is about 2%, minus 2%. And so the value, the naive value at tree level is 0.22, but the actual value when you compute these diagrams is expected to be 2% less than that. Now, how do you find bottom quarks? Well, remember I told you that quark events look like this with 2 jets. There are a lot of tracks. You have to somehow look inside that to find the bottom mesons that contain the bottom quarks. A property of a bottom meson is that it has a long lifetime. Now, long is not probably long in human terms. The lifetime of the bottom quark is 1.5 picoseconds. But when you multiply that by the speed of light, you get a whole 0.5 millimeter. And so if you have precise tracking around the interaction region, you can find a decay vertex of some tracks which, with a relativistic boost, is separated by several millimeters from the interaction point. And this basically just shows the ability of, again, this opal experiment to do that. So the doubly hatched curve are the light quarks, which really come from the interaction region. The hatched here are the charm quarks, which have a lifetime 5 to 10 times smaller, depending on which meson you talk about. And then the bees have a relatively long lifetime. And so what you then do is you put a cut here somewhere. This is a log scale, so you measure the vertices out there, and then you determine the fraction of events that are associated with these bottom quarks. And yeah, it works. Instead of 0.22, you get 0.216. And that's that 2% shift. And please notice that the accuracy of that is 0.3%. So you've really measured it extremely well. Actually, it turns out you can also measure the fraction of charm quarks. That's not so accurate. The slide that I whisked through shows you how to do that. Okay. Now we come to the Z asymmetries. You remember the branching ratios are all about the same order of magnitude, but the asymmetries are very different. It's 15% for leptons, but maximal for bottom quarks. Does nature know about that? Well, let's first talk about the leptons. There are basically 3 ways to measure the lepton asymmetries. The first is using forward-backward asymmetries. The second is using a direct measurement using beam polarization. And the third is using special properties of the weak decays of the tau lepton. And all 3 of these methods were used in the LEP program. So let's go through them. For unpolarized beams, the angular distribution depends on the helicity of the particles coming in and the helicity of the particles going out. As you would know if you studied very carefully chapter 1 of my textbook. So if you take what's in that chapter and you use the fact that the weak interactions are parity asymmetric, you would come to this formula where the left-handed electrons going in and left-handed muons, let's say, coming out, gives you a 1 plus cosine theta squared distribution multiplied by the fraction of z events that have that. If you add it all up, you find that the forward-backward asymmetry is proportional to 3/4 times the electron asymmetry times the AF, whatever is the asymmetry of, if it's muons, that would be A mu. And then you can measure that asymmetry. Of course, for leptons, this is a really small number. This is 15% squared. But nevertheless, if you have enough data, you can measure that quite accurately. Here's a more interesting way to do it. If the Z has a different coupling to left-handed as opposed to right-handed spinning electrons, you should be able to see that by preparing an electron beam which preferentially has the left-handed orientation. So how do you do that? Well, it was done at SLAC with this interesting apparatus. Here's the electron source, so that's a cathode. You put a negative charge on that, electrons come out, you catch them up in the accelerator or beamline, and you accelerate them. A special cathode was built, which is made of a material called strained gallium arsenide. You put enough germanium in there to distort the lattice structure, and what it does is split the spin states of the electron bands. Then when you hit that with laser light, depending on the laser polarization, you would kick out preferentially left or right-handed spinning electrons. The laser is prepared here with linear polarization. And then there's a thing here called a Pockels cell, which if you put a positive voltage on it, it's a plus quarter wave plate. And if you put a negative voltage on it, it's a minus quarter wave plate. So essentially a random pattern of circular polarization comes out here, and then corresponding to that pattern, the electrons are kicked out. Now the next thing that happens is that they go into the SLAC, the linear accelerator. They go 3 kilometers. They then go into a transport line, which takes them another kilometer. Then they hit a positron beam, and it annihilates. So it's really cool. You put a signal on the Pockels cell, and 4 kilometers that way, you see the Z cross-section change. And it's very elegant. A lot of systematic errors cancel when you do that. And here's the final number. The asymmetry is 0.1513 with the error in the third decimal place, as you see. One more cool way to do this is to look at tau polarization. So the tau is, of course, another kind of lepton. Fundamentally, it's the same as the electron and muon. It participates in the same weak interactions. The prediction of those couplings from the standard model is exactly the same as for the electron and the muon. However, the tau is heavier than the electron and the muon. It weighs about 1.8 GeV, and therefore it has the ability to decay into a lot of states that muons, for example, can't decay into. Muons basically just decay to electrons and neutrinos. But for the tau, one has other possibilities, and here's a really cool one. The tau going to a tau neutrino and a pion. Now, let's say you have a tau which has its spin polarized in the left-handed sense, as I've shown here. Neutrinos are always left-handed polarized, or at least the non-sterile ones, the ones that participate in the weak interactions. And so the neutrino always goes in the tau direction so that its spin can be aligned with the original spin of the tau. The pion takes the recoil, and therefore it has to go backwards, or at least be slower in this frame. So the rule is left-handed taus go to slow pions, and if you reverse everything, right-handed taus go to fast pions. So you measure the energy of the pions coming out of Z decays, and here's what you find. It's the left-hand diagram here. So if the Z were totally parity symmetric, this would be flat. This is the contribution from the left-handed taus. This is the contribution from the right-handed taus. And as you see, there's a significant difference between them, which when you put in the numbers turns out to be the same 15%. And by the way, you can do this with many tau decay modes. The story is a little more complicated. Here's the corresponding red and green distributions for the decay of the tau to a muon. When you put everything together, oh, and there's one more thing. There's a correlation between the tau polarization and cosine theta that you can also use. So when you put everything together, you get many measurements of this AL. And I remind you that from my formulae, AL is approximately equal to 8 times a quarter minus sine squared theta W. And actually, sine squared theta W is pretty close to a quarter. So you measure that number very accurately. And so here's the final number that comes out, 0.23. That's what I quoted you before, 153 with the error in the fourth decimal place. And then that number, as you see, is in very good agreement with all these different methods of measuring the lepton asymmetries. So these are the three that I just talked about, and there are several more of somewhat lower accuracy. Now, I told you that the lepton asymmetry was supposed to be 15%, but the asymmetry for down quarks was supposed to be almost maximal. So is that true? Well, how would you do that experiment? Well, one way to do the experiment is you remember what I told you a few moments ago, that a left-handed spinning electron turning into a left-handed spinning thing has a 1 plus cosine theta squared angular distribution, which means that all the products go forward. On the other hand, a right-handed spinning electron going to a left-handed spinning thing, all the decay products go backwards. So if I prepare a left-handed electron beam and I make down quarks, the prediction is they're all left-handed, so they all mainly go forward. If I prepare a right-handed spinning electron beam, they would all go backwards. So what does the data say? Well, the data, unfortunately, is not perfect because you can't always tell a bottom quark from an anti-bottom quark. There's another art to that. If the bottom quark decays to a muon, it'll be a mu minus. if the bottom quark decays to an electron, it'll be an E minus, whereas the anti-bottom would decay to an E plus. But that only happens 20% of the time. And other than that, you have to use some more imperfect measures. But nevertheless, there should be a dramatic effect. And here's the data. So this is cosine theta. This is the angular distribution, including the effect of this confusion, if you can't tell the particle from the B from the anti-B. And as you see, it's pretty dramatic. The bottom quarks go forward with a left-handed polarized beam, and they go backward with a right-handed polarized beam. And if you estimate the confusion, it turns out that the AB is about 0.93, very close to the standard model prediction, and within the errors of the standard model prediction. Okay. So here's a summary, which includes these measurements and several more, of the various determinations of the properties of the weak interaction, mainly from this precision Z experiments done at CERN, at the LEP accelerator, and at SLAC. And frankly, if you look at these numbers, it's really pretty impressive. The error bars, in all cases, are percent level, in some cases, parts per mil. This is the measurement. This is the best fit to the standard model. So of course, you don't know a priori what G, G prime, and V are, but you can fit them to this data. And so these are the numbers represented by the best fit. You see, in all cases, in very good agreement. This is a visualization of the discrepancy in terms of sigmas. So you see, I guess, here and here, there are a few sigma discrepancies. But in a list that large, you would expect 1,3 sigma discrepancy. So it really does confirm this simple SU2 cross U1 model in a very remarkable way. Not only does the model make sense, not only can we write it in a textbook, but the experiments say that it really does represent nature at a very high accuracy. So now, there's another chapter in these notes which is about radiative corrections. I think it's a little too long to discuss. So is it okay if I stop here for the moment? And I'll put these slides on the web somewhere. Yeah, and then those of you who would like to read through the last slides, I can answer questions about them. This is about, for those of you who are a little cognizant about particle physics, about the parameters called ST and U, which parameterize the deviation of precision electroweak from the standard model. So there's a chapter on that in the slides that I'm not going to do for you. And well, maybe except just to show you, this is the current status. ST and U should be 0 if the standard model is correct. An order 1 deviation in ST and U corresponds to a 1% measurement. So you see the errors are really at the few tenths of percent level. The 0 point is in here, so it's in good agreement with the composite of these measurements. And well, whether you like it or not, no observable deviation. So the standard model works extremely well for the corpus of precision electroweak data. Okay, so as I say, we have very high confidence that the weak interactions are described by this SU2 cross U1 theory. Of course, this now brings new questions, which I'm going to discuss in the next lecture. The only way within that theory for W and Z bosons to get mass is by this complicated arrangement of things. First of all, you need a Yang-Mills theory, and then that Yang-Mills theory has to be spontaneously broken. And how does that happen, and why? So that's a very important question, and that's what we're going to discuss when we come back from the coffee break. Okay? Thank you. So if you have questions on this, you should ask them now. Please. Yes?
So the top levels of them are quite different.
Here, I'm sorry. Oh, yes. Okay. Yeah, there are 15% more events in that diagram than that diagram, right? And that's because of the leptonic asymmetry. If you use a left-handed beam, you get 15% more Z's. Ah. So that's another way of measuring one of the things I told you about before. It's not as accurate, but it's the same effect. Other questions? If you're wondering about something, the answer might be as easy as that. So please ask the question. Yes?
You were mentioning about colliding positron and electron, but they are highly, their positions are highly uncertain. How do they achieve to collide them?
Well, the positions are not highly uncertain. Well, of course, you don't know exactly where the positron and the electron are. You have to collide. You can't have that much control. So in an accelerator, typically what you have is a let me draw it as a cylinder, but actually it's a Gaussian distribution. You have a bunch of electrons with a certain density, and you have a bunch of positrons with a certain density, and you try and understand the shapes of these distributions, and then you shoot them at each other. And then randomly, an electron in this bunch will be head-on with a positron in this bunch with a probability that you can estimate. So this is what the cross-section is. I mean, the rate is always going to be the sigma that we quote times basically the density of electrons that a positron in here sees times the velocity, the relative velocity with which these things come together. Okay. So in that way, you don't have to know that an individual electron is hitting an individual positron. It's all statistical. Now, originally I thought you were asking a different question, so I'll answer that too. Of course, there's some quantum mechanical uncertainty in the position of any electron or positron. But if you work out the numbers, it's extremely small. The size of these bunches for example, the SLC experiments is about a micron. So actually, it's no small feat to take bunches over kilometer scale regions that are of micron size and actually have them hit each other. That's a problem. If you find that problem fascinating, you should become an accelerator physicist, because you have to be.
In a chamber, it's just micron size.
Sorry?
The chamber is micro size.
No, the chamber is about a centimeter in radius. But the actual beams, the little bunches are micron size.
Cross-section.
Yeah, across. So you have to bring those together. And actually what they do is you can, if the bunches miss each other, they deflect. And it's a macroscopic deflection, you can measure it. And then when they begin to interact, there's a lot of forward radiation that you can also measure. So using those tools, you can zero them in on each other. And I'd like to remind you that California is an earthquake region. So you really have to, eventually have a computer manage that process of zeroing the beams together in real time. Okay. Anyone else? Yes?
Before you were talking about constraining the number of neutrinos,
Yes.
does it make any sense to interpret it as a fraction of a number of neutrinos? Or when you look at the number 2.9 plus something, you interpret that as 3 and that's it? There are a couple ways in which that makes sense. One way is if you have sterile neutrinos, then the neutrinos that we observe, so the Z doesn't care what the mass of a neutrino is.
as long as that mass is much less than the z, and remember, real neutrino masses are of order of tenths of an eV. Okay, as long as the mass is down there, it's irrelevant what the mass actually is. But what can be relevant is the mixing angle. If there are sterile neutrinos, and the 3 standard model neutrinos mix with sterile neutrinos, then you'll get a slightly lower number of neutrinos measured than 3. In a similar way, if there's a 4th neutrino, but it's, again, got a fraction of the strength, you could see a fraction of it. So that's a kind of theory you can make. Another kind of theory you can make is the Z has other invisible products. For example, if there are milli-charged particles, and those particles have neutrino partners, then we put a limit on the existence of such particles. Although, frankly, it's not a very strong limit compared to other limits on milli-charges. And then there are also ways that you can radiate bosons, invisible bosons in ZDKs. So basically, this number just accounts the excess invisible width. Okay, the difference from 3 is an excess invisible width, which might be positive or negative. And there are, many, many ways to interpret that theoretically. But yeah, it really makes sense to quote a fraction with high accuracy. Okay. Anyone else? Okay. I will try and put these slides on the web somewhere, and you can go over them in your spare time. If you have a question tomorrow, I'll be around. Meanwhile, I should say thank you and goodbye, except we're going to be here in 10 minutes for the next lecture, so I'll see you then.